In this video we're going to look at field effect transistors. So transistors can switch or amplify electrical signals, and they use both p-type and n-type semiconductor materials. And resistors are often referred to as solid state because they have no moving parts. So normally electrical switches have to be mechanical so that they open and close an electrical contact to switch things on and off. But that's not the case with transistors. Semiconductors have an intermediate electrical conductivity, typically 1 to 100 ohm meters for their resistivity, and that's between the sort of resistivity that you expect for an insulator and a conductor. Now, semiconductor materials used in transistors include p-type silicon and n-type silicon, so we're going to have to try and understand what these are. So in silicon there are 4 outer electrons, and if we put those into a crystal lattice, those outer electrons are shared with its nearest neighbour in order to form covalent bonds. Now for p-type silicon, it's doped with a group 3 element at very low levels, circa around 1 ppm. So for example, it could be boron. So if we draw this structure again, the boron only has 3 outer electrons, which again it shares with the silicon surrounding it to form covalent bonds, but there's 1 electron missing that forms what we refer to as a hole. So this hole arises from the missing electron and is almost like a positive charge that sits there, and electrons can then hop into that vacant space. And this is the way that p-type silicon actually conducts electricity, through the migration of these positive holes. N-type silicon, on the other hand, is doped with a group 5 element. Again, very low levels, around 1 ppm, and for example it could be phosphorus. And if we put that into the structure, what we see is that because phosphorus has 5 outer electrons, 4 of them form covalent bonds with the silicon atom surrounding it, leaving 1 electron free to move around. And in an n-type semiconductor, the conduction occurs via the movement of the free electrons. Now, in a field effect transistor, we have a source where the charge enters the transistor, a channel through which the charge can flow, and a drain where the charge exits the transistor. The current flowing through the field effect transistor is influenced by the voltage applied to the gate. So here we have an overall diagram with all of those components put together. So we have the source, which could be n-type or p-type, but in this case we've made it n-type silicon. We then have the channel, which has to be the opposite type, so in this case it's p-type silicon, and then back to n-type silicon for the drain. The gate is a strip of metal that's separated from the channel by a thin electrical insulator made typically of SiO2. Now, electrons enter through the source, travel through the channel, and then exit via the drain. And if we apply an electrical potential to the gate, that will affect the conductivity through the channel. So if we apply a positive charge there, those positive charges on the gate will now repel the charges that are in the channel, and that will start to affect the conductivity. If we increase the charge even further, the repulsion effect becomes even stronger, and the resistance through the channel is affected even more. So that's the basic principle of how a field effect transistor works. That a positive electrical potential being applied to the gate will repel the positive charges in the p-type silicon and therefore affect the electrical resistance through the channel, and that will affect the current flow from source to drain. So that's been a video about field effect transistors. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.